The thing about collisions is that they very rarely occur in one dimension. This section we are going to discuss momentum in 2 dimensions. Remember that momentum is the mass of a moving object multiplied by its velocity. Also keep in mind that the total momentum before a collision is equal to the total momentum after the collision, and that sometimes the kinetic energy is conserved. There are a lot of collisions out there that do not happen in a single dimension. In this case, we need to take the angles into account. Playing pool is a good example of collisions in more than one dimension. The red ball in this case is stationary to begin with, and so has a 0 velocity and therefore 0 momentum. The purple ball is moving towards the red ball at a certain velocity 1. For simplicity's sake, we will call the initial direction of the purple ball the x-axis. Unless there is a direct hit, when the balls collide, one ball will move off in one direction and at one velocity, and the other ball will move off in a different direction and a different velocity. In a one-dimensional collision, we simply add the momentums together and go on our way. In the case of 2-dimensional collisions, we have to take into account the fact that the momentum is a vector. Momentum is conserved, but only in the specific dimensions in which it operates. In this case, we are operating in 2 dimensions, x and y. So momentum is conserved in the x direction, and it is also conserved in the y direction. We simply cannot use the equation for conservation of momentum in this case. If we consider the new motion of a stationary ball, we see that after the collision, the ball moves off in a direction at some angle to the original horizontal motion. The velocity of this ball can be described as at an angle to the x direction, which we call theta. We need to calculate the component magnitude and direction of this velocity. We can drop a perpendicular line to the x-axis and one to the y-axis to determine our component vectors. Remember that cosine is adjacent over hypotenuse. In this case, the x component is divided by the hypotenuse and is equal to the cosine of the angle. The y component is opposite over the hypotenuse, and so we would use the sine of the angle theta to determine this value. Of course, we can clean these up a bit to make these equations a bit neater. The x component of this velocity is equal to the velocity times the cosine of the angle theta. The y component of the velocity is equal to the velocity times the sine of the angle theta. If we go back to our pool table, we have ball 1 with a mass of m1 moving along the horizontal axis at some velocity v1, towards ball 2 with a mass of m2 and a velocity of v2, which in this case is 0. After the collision, the 2 balls travel off with new velocities in different directions, theta 1 and theta 2, with respect to the x-axis. We need to resolve these components into their respective x and y directions. Ball 1 is initially traveling along the x direction. We can describe that angle as 0. Cosine of 0 equals 1, so the velocity of this ball is just v1 times m1. Ball 1 is initially traveling along the x direction. We can describe that angle as 0 with respect to the x-axis. The cosine of 0 is 1, so the velocity of this ball is just v1. The momentum of this object is m1 times v1. The total momentum of ball 1 equals m1 times v1. Ball 2 is not moving, so its momentum in the x direction is 0. The total momentum in the x direction before the collision is m1 times v1 plus 0. This is equal to the total momentum in the x direction after the collision. Momentum after the collision must take into account the angles we just described. The momentum of the first object is the mass times the velocity times the cosine of the angle theta. The momentum of the second object is mass times its velocity times the cosine of its angle theta. That gives us the values for the x component for each momentum. Now let's look at the y component. Ball 1 is only moving in the x direction. It has no y component, so we use 0. Ball 2 is not moving yet, so its y component is also 0. After the collision, we can determine the y component of each ball by taking the mass times the new velocity times the sine of their respective angles. Notice that ball 2 is moving in the opposite direction of ball 1. Its y component is going to be opposite, or negative, of ball 1.